stop overfitting with L2 regularization in Python. By the end, you will see how a simple penalty stabilizes coefficients. You will build a tiny regression demo that fits, overfits, and then corrects with L2. You will also learn how to pick a penalty that balances bias and variance. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Overfitting shows up when a model learns noise instead of signal. You see perfect training scores, but poor holds out performance. L2 regularization fixes this by shrinking weights toward zero, so the model favors simpler explanations. It is used when models have many coefficients or when features are noisy. A downside is that strong L2 bias can underfit and erase subtle patterns. So we tune a penalty. I will use the same small noisy polynomial dataset throughout to keep comparisons clear. In plain terms, L2 pushes large coefficients down. Think of coefficients as levers. L2 adds a cost for long levers. Shorter levers mean smoother, more stable predictions. With a tiny data example, you will see how a plain linear fit, a flexible polynomial fit, and then a regularized polynomial differ in behavior. We will fit models, compare train and test error, and search a small grid of penalties to pick the best ridge value. Now we will fit a tiny linear model and inspect its slope and intercept. This snippet fits a tiny linear model and prints its slope and intercept. It shows the baseline where a simple straight line tries to explain the noisy quadratic data. The goal is to establish a simple reference so you can see what happens when we allow more flexibility. If the slope and intercept change a lot when we add polynomial features, then you are already seeing the sensitivity that leads to overfitting. This snippet is intentionally small, so the slope and intercept are easy to interpret and compare against later models. Next, we let the model get very flexible so we can watch overfitting emerge. This snippet fits a high-degree polynomial without regularization and shows training error. It demonstrates how flexible models can drive training error very low by matching noise. The polynomial transform creates many correlated features, and the linear solver assigns large coefficients to fit tiny wiggles. Training error looks great, but this is deceptive. Large coefficients are a sign of instability. If you increase the degree, you will reduce training error further, but you will also amplify sensitivity to noise and small changes in the input. Now we will measure how this flexibility breaks on new data by comparing training and test error. This snippet measures train versus test error to expose overfitting behavior. It computes mean squared error on both the training split and an independent test split, so you can see the divergence. When the flexible polynomial fits noise, the training error drops, but the test error rises. That gap is exactly overfitting. Watching these two numbers lets you judge whether a model is learning real signal or just memorizing quirks. If your test error is higher, you need more regularization or less complexity. Next, we introduce L2 regularization to tame those coefficients. This snippet applies L2 regularization ridge to shrink coefficients and stabilize predictions. It fits the same polynomial basis, but adds a penalty proportional to the sum of squared coefficients. The result is smaller, more evenly distributed weights, and smoother predictions on the test set. Changing the penalty strength moves the model between two extremes. A tiny penalty behaves almost like no regularization and keeps high variance. A large penalty forces coefficients towards zero and increases bias, but reduces variance. This snippet shows the trade-off and how L2 improves test error relative to the unregularized model. Now we will search for the penalty that best balances bias and variance on our small dataset. This snippet searches a small ridge grid and reports the best penalty and error. It fits multiple ridge models across a handful of penalty values and evaluates test performance for each. The search reveals a valley where test error is minimal. That valley tells you the penalty that balances underfit and overfit for this data. A finer grid or cross-validation would refine the choice. Reporting the best penalty gives a concrete number you can reuse as a starting point for similar datasets or for a larger model. Recap in 3 crisp points. L2 regularization is a penalty that shrinks coefficients to reduce variance. Use it when models have many features or when test error outpaces training error. One caveat is that too much penalty causes underfitting and wipes out meaningful signal. Next step. Tune the ridge penalty more thoroughly with cross-validation over a wider grid and record train, validation, and test errors to confirm stability. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.